In order to understand what scriptable objects are, it can help to visualize the three possible places that scripts can exist in your game. They can be components that are attached to objects, they can be static classes that exist in your project, or they can be data structures, such as plain classes, that exist inside of another script or function as a variable. You'll learn more about scripts that act as data structures in the lesson on structs and plain classes. For now, I want to focus on the difference between component classes and static classes. Component classes are attached to objects and can exist as multiple instances, where each instance of a script holds its own unique data. Because of this, in order to interact with a component, you need to know which one you're interacting with, meaning that you need to get a reference to it. Static classes, on the other hand, exist in the project, and just like static functions and static variables, they're accessible from everywhere, but cannot be duplicated, meaning that it's not possible to create an instance of a static class. So what can you do when you want to store instances of data outside of your scene? This is where scriptable objects can be useful. Even if you're very new to Unity, chances are you've already used a data type that works in the same way as scriptable objects do. Assets, such as audio clips, materials, and textures, exist in the project, not the scene. It's possible to create multiple assets of the same type, and they can be easily referenced from components in the game by dragging and dropping them to a field. And because assets exist in the project before the scene is ever loaded, this means that a particular asset can be set in a prefab object by you, even if the object that references it doesn't exist in the scene yet. Scriptable objects work in the exact same way. They are essentially script assets, instances of data that are created using a template that you set up, that exist in the project but that can be used by objects in the scene. There are two steps to creating a scriptable object. First, you'll need to create the script template, and then you'll be able to create asset instances of that data type. For example, let's say that I wanted to create a set of weapon stats. To do that, I'd need to create a new C# script, and then add in the data that I'd want to use, such as the weapon's damage and fire rate. At this point, I could also add a game object reference for the type of projectile that this weapon should shoot, or an icon that I could use to display this weapon choice in the game. However, right now, this is just a normal monobehavior script. Two things need to change to turn this into a scriptable object that can be used. First, I need to have the script inherit from Scriptable Object, not monobehavior. Next, I need to add the Create Asset menu attribute, so that an instance of this type can be created using the Create menu, or by right-clicking in the project window. Technically, this isn't required to create the scriptable object, but it is required to use it, as this is how you'll create new instances of a scriptable object type. In Unity 6 and later, it's possible to carry out these two steps automatically by creating a new scriptable object script instead of a monobehavior script. This will also add optional parameters to the scriptable object, which determine what a new asset of that type is called by default, and the menu path, which can be useful if you're using a lot of scriptable objects and you want to organize them into subfolders in the Create menu. Once you've created an instance or multiple instances of a scriptable object, you can set its data in the inspector. In your game, other scripts can use the scriptable object in the same way as any other asset, by declaring a variable of that type and accessing the scriptable object's public data. In simple terms, this is all scriptable objects do. They allow you to create referenceable assets of the same data type. But you might be surprised by just how useful that can be. So what can you do with a scriptable object? One of the most common uses of a scriptable object is to create a kind of data profile, such as stats about an item, a set of sounds for an object, or a settings profile that can be set by you in the inspector and then used by other scripts in the game. You'll have seen a similar kind of functionality in many of Unity's own systems, such as post-processing profiles. This is what scriptable objects are ideal for, to create a kind of data that is used by scripts in your game, and then create instances of that data type that can be plugged into another system. For example, let's say that you want to create a damage profile for different kinds of enemies in your game. There are a couple of ways you could do this. For example, you could enter the damage information directly into an enemy script, and then create multiple enemy prefabs. If each enemy prefab has a unique damage profile, meaning that there are as many different damage stats as there are enemy types, then this would work, and there's no real need to split it up any further. But what if you have many different types of enemy, but only a couple of different damage profiles, such as small, medium, and heavy, for example? Now it makes sense to use a scriptable object, which would allow you to define 3 types of enemy damage and then just plug them into any enemy that you create. The point of this is that it's very easy to manage. If you want to change how much damage heavy enemies do, for example, you can do it in one place. Otherwise, you'd need to go into each enemy's script to change the data manually whenever you wanted to adjust it. This particular use case works well because the number of damage profiles is less than the number of different enemies. However, the inverse can also be true. If you have one weapon script, but many types of weapon profile, it's possible to put the functionality of your weapon in one place, the monobehavior component, and the data that will actually change, such as the damage and the type of projectile that's fired, in a scriptable object. And because the scriptable object is an asset, that same data can be referenced by other systems in other places, such as the pickup that enables the weapon type. Meaning that if you wanted to change the weapon's icon in both the pickup and the UI, you could do it in just one place. This is a traditional use for scriptable objects, and it can be extremely useful for making the content of your game. Want to make another weapon? Make another scriptable object, change the data, and you're done. But because of how scriptable objects work, it's also possible to use them to connect data in your scene. Unlike monobehavior instances, scriptable objects can be accessed globally, meaning that any object in the game can use any scriptable object in the same way that any audio source can access any audio clip, by dragging the asset to a field in the script that you want to access it from. Now you might be thinking, if you still need to drag and drop a reference to the scriptable object in the inspector, how is that any different from connecting 2 monobehavior scripts together, since you're still creating a connection yourself? The difference is that because scriptable objects exist permanently, because they're assets, it's possible to set up their connections ahead of time in a prefab. Let's say, for example, that you want to connect the player's health to a UI health bar. One way to do this is to connect them directly, but in that scenario both objects must exist together, either as part of the same hierarchy or separately, where one object must find the other to create the connection. Either way, the 2 objects are coupled and are dependent on each other. Alternatively, you could connect both the UI and the player to one scriptable object that contains information about that player specifically. This works because the scriptable object exists as an asset, meaning its existence is guaranteed. It's there before the scene is loaded, and it will be there after it's closed. As a result, the scriptable object becomes a layer of abstraction between the multiple scripts that read and write the same information, meaning that they don't need to communicate with each other directly. Practically, this means that the UI doesn't care if the player object exists anymore, and neither does the player. Instead, the player writes live data to the scriptable object asset, such as how much health they have, making it available for any other system to read, but importantly, without creating a direct connection between the 2. There are some considerations to make when using scriptable objects to manage live data. For example, scriptable object data is persistent, meaning that when the scene changes, the scriptable object data doesn't. Which makes sense. After all, they're assets, not in-game objects. What this means is that if you're using a scriptable object to keep track of in-scene data, you'll need to remember to reset it yourself. This can be a little tricky, since even though event messages such as awake and onEnable are called on scriptable objects, they work in different ways. Awake is called when the scriptable object is first created, while onEnable is called when it's first loaded. This means that if you want to use a scriptable object to track game data, you'll typically have to manage it from a monobehavior script, such as a player script, to keep the life cycle of data in step with the game's other events. But even though it's not technically what scriptable objects are designed for, using them in this way can be extremely useful for connecting more and more systems to the same set of information, without making them dependent on each other. And while this isn't the only way to do that, there are other methods, such as using events, for example, which you'll learn more about later in this module. The benefit that I'd like you to focus on in this example is that decoupling of data. Specifically, it's the ability to entirely remove one part of a system without breaking the rest of it in the process. This is fundamentally what makes a project easy to change, which in turn makes a project easy to work with, and will be a key component to many of the lessons in this advanced module. So far, we've covered scripts that exist as components in the scene, and globally accessible scripts that exist inside of your project as static classes or as scriptable object assets. However, it's also possible to use scripts to create your own types of data. This allows you to create your own kinds of variable, such as combinations of data, items, and multiple choice options and settings. Generally, there are 3 ways to do this. You can create an object variable using a plain class, so that's a class that doesn't inherit from monobehavior. You can create a type of value using a struct, or you can create a set of named options using an enum. Each of the 3 methods works in a slightly different way, and each has a different use case. However, of the 3, plain classes and structs, which in some cases may appear to work in the exact same way, can sometimes be tricky to tell apart. So when would you use a plain class, and when would you use a struct? What are enums for, and why would you even use a custom data structure in the first place? To answer that, we're going to look at structs first. The easiest way to understand what structs are and how to use them is to look at where they're already used in Unity's code, which is everywhere. Vector values, colors, rays, quaternions, if it's a type of value that isn't a simple type, then it's probably a struct. Which is exactly how structs are commonly used, as custom values. Meaning that if you want to combine multiple pieces of information together into a data type that's easily passed around, such as in a function, or that exists in a class as a variable, then a struct is usually a good way to do that. For example, let's say that you'd like to create a list of high scores, combining a string for the player's name and a number for the score itself. On their own, there's no way to combine the 2 pieces of information. That is, unless you place them both in a struct. Like all of the methods in this lesson, the struct itself can be declared in its own script file, or it's possible to declare a struct inside of another class, either below it or inside of it, which can be useful if you only want to use the struct in one place. While marking the struct as serializable will allow you to view it in the inspector when it's declared, allowing you to create a list of high scores, for example, where each entry is a combined set of information. This is what structs are good for, and whenever you want to combine pieces of data together inside one value, making it easier to use or pass around, a struct is probably a good way to do it. They work in the same way as values, meaning that they're copied, not referenced, and usually don't create any garbage when they're used. However, because they're values, a struct cannot be null, in the same way that a number can't be null, meaning that if you want to create a kind of value that can be empty, such as an inventory item slot, for example, you'll need to use a plain class instead. Plain classes, meaning classes that don't inherit from monobehavior, work in almost the exact same way as structs do. The difference is that a plain class works like a reference type, not a value type, meaning that it can be null. If you remember back to the lesson on variables, reference types are pointed to, meaning that when you assign one reference to another, you're creating a second reference to one data location. Value types, on the other hand, are copied when they're assigned, meaning that if the original is changed, the copy doesn't. This is how structs and plain classes work, where a struct can be considered a value that's copied, and a plain class is an object that is referenced. However, on the surface, this can be confusing. For example, if you serialize a plain class variable, meaning that you can see it in the inspector, you might expect to find an empty reference like you would when creating a reference variable to an asset or an object. But in this case, serializing the variable means that it is no longer null. It's initialized with default data, meaning that on the surface, it's easy to assume that structs and plain classes work in the exact same way when they're serialized, when really a plain class, unlike a struct, can be empty, only if you don't serialize it. But if you don't serialize it, how can you set its data? To do that, you'll need to use a constructor. Constructors are functions that can be used to set up a class or a struct when it's created. They allow you to set the class's data by passing in information when creating a new instance of that type. You've probably already used constructors before, such as when creating a new vector3 which requires you to pass in the x, y, and z components of a value when creating it. You can use your own constructors to set new script data in code. A constructor is simply a function with the same name as its enclosing type and no return type. It will typically be public and can be overloaded, meaning that it's possible to create multiple constructors with different argument patterns. The constructor's parameters are the values that you will pass in when creating an object of this type, and can be used to set up the class's data. At this point, in Unity at least, structs and classes will start to behave in different ways. When using a constructor with a struct, you'll need to account for all of its variables, making sure that they are initialized using constructor data or using default data that is set in the constructor function. Without the constructor, each field will be initialized to its default value. But it's not currently possible to initialize a struct's variable to a starting value in the same way that you would with a class. Meaning that if you want to give a struct initial data, you'll need to use a constructor function to do it, in the same way that you'd need to create a new vector3 value, or a new color, or a new ray, by passing in the data you want to set. Classes are generally a little more forgiving. While they can be set up in the same way, fields that you don't initialize in the constructor will automatically initialize using default values, and it's possible to set the value of a variable when declaring it, meaning that you can give a class some starting information without using a constructor. However, depending on how you're using the class, you will probably still want to use a constructor function. This is because to get the benefit of using a plain class, specifically that it can be null, you won't be able to change its data in the inspector, meaning that you'll either need to use a constructor function or set the object's data after it's been created. So when should you be using plain classes? You'd typically use a plain class instead of a struct when you want to create an object, not a value. An example of this might be an inventory item when you want to create a referenceable instance of an object, but you want it to exist inside of another script, in an inventory slot, for example. A plain class could be useful for this for two reasons. One, it allows the inventory slot to be empty, as in null, and two, it means that the object you create is a unique instance, meaning that it can have its own data, such as condition, ammo, or another kind of value that is specific to an individual instance of an item, not just its type. The last of the three methods in this lesson works in a very different way to the other two, but is likely to be used in similar circumstances to create your own kind of data. Enums are essentially just numbers with human-readable labels. The point of this is to create options that can be set or easily compared to one another. Typically, you'd use an enum when you want to select something or describe something's state, but using a boolean isn't appropriate. Examples of enums include states, modes of operation, and option settings. You'll also find them in many of Unity's built-in functions, such as the force mode setting of the apply force method and the query trigger interaction setting of a raycast function. So when should you be using them? Generally speaking, enums work well for creating a selectable, comparable value that would be difficult to describe using other formats, such as compass directions, difficulty settings, or states, where the value itself doesn't need to contain any information, it just needs to be distinct from others of the same type. For example, it's possible to create a difficulty enum with 3 choices: easy, medium, and hard. This can be used in 2 ways, as a variable that can be set and a possible choice that can be compared against. Enums are just numbers behind the scenes, meaning that if you change the order of an enum's elements, the automatically assigned numbers will change as well. This means that an already selected enum on a script may also change. As a result, it's always best to avoid adding new options to an enum that's already in use, and if you do need to only add them to the bottom of the list. However, this usually only happens when an enum is using implicit values, meaning that it's using the default values that are assigned to each element automatically. Instead, it's possible to manually assign a number to each enum selection, meaning that their values and existing selections won't change even if the order of elements does. It's also possible to create multiple choice enums. To do this, you'll need to add the system flags attribute to the enum, and manually set each of the enum's values to an incrementing power of 2. This is because, like layer masks, multiple choice enums use the binary representation of a number to identify which options are selected. You can then use the hasFlag function to check if an enum has a particular value set. One of the most important elements of this advanced module is decoupling, which, put simply, is the process of reducing a class's dependency on other scripts. This is especially true for indirect connections between your scripts, which are things that may happen as the result of something else occurring, but that are not the responsibility of that individual script to carry out. For example, an enemy might call a damage function in a player's health script. This makes sense. It's a direct connection between a script that exists to deal damage and a script that exists to receive it. But other systems will be affected by the damage function being called, such as the health display, for example, which will now need to be updated as well. At this point, you could argue that the health bar too is a direct connection. After all, if the player's health value lives in its health script, then why not connect it to the health bar from there as well? The problem is that now the health script is starting to take on responsibility for the functioning of another system. The damage function doesn't just damage the player anymore, it now updates the health bar too. Now, at first glance, this may not seem like a problem, and in some projects, it may not end up being a problem at all. But the issue with this is that the script is now very specific, meaning that if you ever want to reuse this script as a general health component, not just as a player health class, and put it on an enemy as well, it now doesn't make sense for it to also update a UI health bar. So what can you do? Apart from creating two different kinds of health script, which, using inheritance, is an option, more on that later, you'll either need to make the health bar update an optional part of the health script's logic, or have the health bar constantly check the health value to see if it's changed. At this point, something that used to make sense is now starting to get messy, and you may start to get the feeling that you're doing something in a bad way. Which is true, since both of these options have drawbacks. Triggering the health bar update from the health script means that you probably won't be able to use it on another object that doesn't have a health bar. While polling the health script from the health bar isn't very efficient either, as it would mean checking every frame for something that only happens occasionally. Instead, an alternative option is to use the observer pattern. The observer pattern is a design approach that allows a script, an observer, to subscribe to the events of another class, a subject. This allows an observing class to act in response to things that happen in your game. For example, in this case the health bar is the observer, and updates its display whenever the health script, the subject, takes damage. Now, instead of managing another system's response to its own logic, all the health script needs to do is manage its own data. While the health bar, as well as any other system that's interested in the player's health, only needs to worry about its own data, which it will update in response to the health script's data changing. This decouples the health script from the systems that it might affect, since the health script simply doesn't care what other scripts are doing in response to its logic. Which also means that more and more systems can be set up to respond to one system's data without changing how that system functions. So how does it work? Typically, the observer pattern is implemented with events. Events in Unity generally refer to a type of functionality where something happens and where it's possible for other classes to do something in response. There are a couple of ways to do this, but most implementations of the observer pattern use delegates. A delegate is basically a variable, except that instead of holding a value, it holds a reference to one or more functions. Other scripts can subscribe their functions to a delegate, meaning that when that delegate is invoked, it will cause any function that's subscribed to it to be called in response. Technically, this is still a direct connection, but the difference is that the responsibility for acting in response to something happening has switched from the subject to the observer, while functions that are subscribed to the delegate are only called when it's actually invoked, meaning that the observing script doesn't need to constantly check the subject's data either, implementing the observer pattern. But how do you actually do any of that? How do you make a delegate? The first thing you'll need to do to create a delegate is to define the type of data that it can contain. Specifically, you'll need to declare a type of function, including any parameters that you want the delegate to be able to accept, if any, and the type of data that it will return, preceded by the delegate keyword. This isn't the delegate itself, rather it's a template for variables of this delegate type, which can then be created in the same way as any other variable by declaring a value of that type and giving it a name. It's this variable that is a container for functions that match the same return type and parameter pattern. A function can be assigned to a delegate with the assignment operator. Like a reference, this replaces any existing assignment to the delegate container, meaning that one function can be swapped out for another when using this method. Then, when the delegate is invoked, the function that's assigned to it is called in response. Invoking an empty delegate causes an error, so it's important to check if the delegate container is null before using it. You might remember from the lesson on operators that the null conditional operator, which is a question mark that checks if the preceding member is null or not, doesn't work on object types in Unity. However, it does work with delegates, meaning that you'll commonly see it used in place of a fully written out null check when using delegate types. It's also possible to assign data using the result of a delegate if it has a return type, just like when calling a function, where the data that's returned is the result of the function that's assigned to the delegate. But what if you've assigned multiple functions? It's possible to assign more than one function to a delegate variable. Known as multicast delegates, this is what differentiates between what is basically a modular function slot and an event system, where one trigger can be used to cause multiple outcomes. This works by adding a function to a delegate instead of assigning it, using the += operator, which adds a function to a delegate container but doesn't overwrite what's already there. Then, when the delegate is invoked, all of the functions that are assigned to it will be called. If the delegate accepts parameters, that same data will be passed to all of the triggered functions. And if the delegate returns data, meaning that it has a return type other than void, the data that's given back will be the result of the last function that it triggers. Subscribing a function to a delegate is the basic mechanism of creating your own event system, where one action causes many others to act in response. However, it's important to remember to unsubscribe that same function from a delegate when it's no longer needed, by subtracting the method from the delegate variable, otherwise you'll get an error when trying to call the function. If, for example, the reference object no longer exists. Typically you do this in onDisable, which is always called whenever a script is turned off or destroyed. And when coupled with onEnable, allows you to basically enable and disable a script subscription to a delegate when turning it on or off. If the subscribing function is in the same script as the delegate, then this doesn't really matter, as destroying the script would remove the observer and the subject. But chances are you're likely to use delegates to create a kind of event system between objects, in which case it's more likely that the observer and the subject will be in different scripts. But if they're in different scripts, how can you connect an observer to a subject? Generally speaking, the approach for connecting observers to subjects is the same as when connecting regular functions and data together. You might create local delegates and then connect them through a hierarchical relationship, such as a player's subsystem, or you could create a global delegate, either by using statics, singletons, or through another common layer of abstraction, such as a scriptable object, where the same asset, containing a set of delegates, could be plugged into multiple scripts. The method that you choose is going to depend entirely on the structure of your game, and the normal rules of connecting scripts generally applies to delegates as well. After all, a delegate is not an event, at least not by default. It's just a modular container for a function, a variable that holds methods, not values. Meaning that technically it's still a direct connection between two classes. The difference is that the responsibility of executing a response to something is reversed, where observing scripts manage their own connection to an event, while the subject only needs to worry about triggering it. But delegates do not enforce this relationship by default, and it's entirely possible for an observer or another script to invoke a delegate for the subject, which can make it difficult to keep track of who is the subject and who is the observer. Event delegates, which are simply delegates preceded by the event keyword, can only be invoked by the class that they're contained in. This helps to enforce the observer pattern, where a subscribing script can only observe what a subject does, not trigger it. While delegates are generally very easy to use, they can be a little inconvenient, since declaring the type of delegate that you want to use before you use it can seem a little fiddly. But helpfully, it's possible to use built-in delegate templates, meaning that you don't have to declare your own, in the shape of actions and func types. Actions are essentially ready-made delegates. They allow you to create a simple delegate type without needing to declare it yourself. To create an action, you'll need to add the system namespace and create an action type. Just like when defining your own delegates, it's possible to make an action an event action, meaning that it can't be called from outside its containing class. Actions always have a return type of void and can have 0 or more parameters, which can be added using angled brackets. While func, which works in the exact same way as actions do, can have a return type, again specified using angled brackets. These are generally the easiest two methods of creating delegate-based events in Unity. So much so that you typically won't need to declare your own types of delegate at all. However, there is another method of triggering events in Unity that, depending on how you're building your project, might be easier to use. Unity events are basically serialized events that are managed in the inspector instead of in code. You may have already used them in UI elements, where the onClick and onValue changed events of buttons and sliders is technically a Unity event. It's possible to make a basic Unity event by adding the UnityEngine.events namespace and declaring a Unity event variable. Then, in the inspector, simply connect whatever it is that you want to trigger when the event is invoked. It's also possible to create Unity events that pass data. The dynamic event type can then be used to pass function data through the event when it's invoked, as opposed to static data that can be set in the inspector. Unity events can be extremely useful for creating modular connections between scripts in the inspector, as they allow you to connect one trigger to many different possible functions and classes. Just like delegate-based events, this is useful for keeping a script reusable by limiting its responsibility, since even when using a Unity event, which unlike a delegate is controlled from the subject side, not the observer, the actual code remains the same, meaning that it's easy to reuse on other objects, where the same trigger may cause different things to happen. Over the next 3 lessons, you're going to learn about 3 different techniques for managing the structure of your scripts, including what they're built to do, how they interact with each other, and importantly, how to write them in a way that makes your project easy to keep moving forward. In this lesson, you'll learn about script composition, which is the principle of creating ability-focused scripts that each have limited responsibility. Then, next, you'll learn about inheritance, which involves creating hierarchical structures based on type, and that are used to avoid writing the same code over and over again. After which you'll learn about interfaces, which allow you to communicate with the class based on what it can do, not what it is. Each technique has its own use cases, benefits, and drawbacks, and some techniques, specifically composition and inheritance, are often viewed as alternatives to each other. However, chances are you may find yourself using a combination of all 3 methods when making your game, depending on what it is you're trying to do and the problem you're trying to solve. So let's start with script composition. What is it, and what is it good for? Script composition is a game architecture approach that involves splitting up the functionality of large, multi-purpose classes into smaller, single-purpose scripts that are easier to add, remove, or change. The general idea is that if you can give an object a certain type of functionality just by adding a script to it, and if removing that functionality is as simple as removing the script from that object without anything else breaking, then the different moving parts of your game will be very easy to change. And a game that's easy to change is easy to work on. If you've used Unity at all, then you've already seen script composition in action. Game object components such as cameras, lights, and audio sources are used to give an object functionality, and removing that functionality is as simple as removing that component. By taking the same approach with your scripts, it's possible to mix and match behaviors to create objects that would be difficult to program using a more rigid hierarchy. For example, you might want to give 2 seemingly unrelated objects the same functionality, such as giving both a player and a destructible object the ability to be damaged. With inheritance, for example, this could be tricky, as you'd need to isolate the exact point in the hierarchy where the ability to be destroyed is shared between classes of that type. This might be difficult or even impossible to do, depending on the structure of your objects, whereas with composition, it can be as simple as adding a single script to that object. So what's the catch? One of the hardest parts of getting composition right is knowing what to put in a single script. Generally speaking, each script should have a single responsibility. It should be written in a way that would allow it to be reused on a different object if needed, and it should be self-contained enough that it can be easily added or removed without heavily depending on other systems. This part is especially important since when you first try breaking up the functionality of your object into different classes, it can be very easy to simply write one script in two places. So how can you avoid that? How do you decide what goes in a script and how small it should be? Knowing what to put in each script won't always be clear, and while there are design principles, such as the single responsibility rule, which recommends only giving a script one reason to change, in practice, especially when you're building your first game, this advice can be quite hard to follow. So much so that following the single responsibility rule too rigidly and splitting out your scripts into too many component parts that each then need to be connected together again can make your game harder to build instead of easier, which kind of defeats the point of composition in the first place. Instead, it can help to find a balance between convenience, keeping related functionality within a single class, and modularity, meaning that your project is easy to change. But one size does not fit all, so how can you find that balance? While there isn't a general rule of thumb that works in all cases, one approach is to consider the limit of responsibility for a script. What does that mean? It means that when you're writing a script that potentially does more than one thing, you'll need to ask yourself if those things will ever need to be separate from each other. For example, it's likely that you might combine the functionality of a health script with a damageable script. One allows an object to have health, while the other allows it to take damage. These are two distinctly different tasks, and if you're following the rule of single responsibility, they should be separate. But, for the sake of convenience, you might decide that they belong together. After all, the whole point of taking damage is to remove health, meaning that chances are you probably won't add the damageable script without also adding the health script. In which case, wouldn't that be writing one script in two places? So why bother trying to separate them, if you're just going to have to reconnect them all the time anyway? While the best option won't always be clear or the same between any two projects, the principle of single responsibility can be helpful as a general guide, even if it sometimes feels counterintuitive. In this example, the way in which an object takes damage might be complex, factoring in armor or elemental damage and resistance, while the way in which health is managed might not be as simple as a single value. You might instead want to combine health with other vital statistics such as stamina. There may even be a situation in which an object may only require health, or might only need to be damageable, in which case you'll want to keep each system as its own separate ability. Not to mention the secondary systems that may need to be connected to either script, such as visual effects, health bars, animations, or sounds. However, none of that alone is enough of a reason not to combine the two scripts if it suits you and if it suits your project. Single responsibility or not, if it makes sense to you, do it. After all, the point of composition is to make your project easier to manage, meaning that so long as you consider how difficult something will be to change or adapt later, then you're already halfway there. Generally, however, composition and single responsibility supports this, since being able to recognize what a script can or will do, and how to interact with it just based on its name, can be easier than working with a more general class that does more than one thing, but it's not clear exactly what it does and doesn't do. This isn't for efficiency's sake or for performance or modularity, it's an ease of use consideration, as you are extremely likely to simply forget what some of your scripts do. Which is why sometimes, even if it feels inconvenient, keeping your script simple and separate can make your project easier to work with as a whole, since you'll be able to tell what any one script does and what it's for just by looking at it. Then the only thing you'll need to work out is how to connect them all together. The methods that you'll use to connect scripts together when using composition will be the same as when connecting any two classes together. We've already covered some of these methods, including direct connections, getComponent, and events. It will be up to you to decide exactly how you want to connect your scripts together. However, what's important to consider when connecting scripts using composition is the limit of any one script's responsibility. For example, while a movement script may be responsible for moving an object, it isn't necessarily responsible for detecting the input that causes it to move. Instead, think of the script as a small machine. It has controls, such as public functions, and can provide data, either through return types or events. But generally speaking, what happens inside of the machine is closed off to other scripts. This keeps the inputs and outputs universal, meaning that different types of scripts can interact with this one so long as they provide the right kind of data, such as a movement vector, for example. The benefit of this is that because the responsibility of the movement script is limited, and because the input that it can accept is well defined, it's easy to swap out an input controller for an AI controller instead, without changing the movement script at all. Inheritance is a cornerstone of object-oriented programming, and behind the scenes is used to power many of the systems that you'll use to build your game. But how can it be useful to you? And how will you know when you should be using it? The point of inheritance is to avoid duplication when classes share behavior because they are the same type of thing. For example, let's say that you have a player, an NPC, and an enemy. Each of them has different behavior. The player can be controlled, the NPC might talk to you, while the enemy might attack. However, some of their behavior is the same. They all walk and move in the same way, they all have health, and they can all be killed. But if you wrote one class for each of them, you'd have to put that functionality in each class as well, which would make it very difficult to change as you'd need to go back into each script to rewrite it. Using inheritance, it's possible to put their shared logic in a base class that each of the other classes inherit from. This allows the different types of human to all use the same functions for the logic that they share, replacing or extending it if they need to do it in a different way, ultimately making it much easier to manage and, importantly, easier to change. While this is an oversimplified example, and not necessarily a structure that you'd use in your game, it highlights the general idea behind inheritance, which is that when you're creating a class that shares some of its behavior with another class, inheritance can help you to avoid writing the same code in more than one place. But inheritance is only useful when it's used in the right way, meaning that it's important to know when to use it and when not to. So when can inheritance actually help you? Inheritance is generally pretty easy to use. What can be difficult is knowing when to use it. For example, the previous player, NPC, enemy example is useful in that it highlights the point of inheritance, but isn't necessarily an option you'd want to use, since depending on how you're structuring your game, you probably don't want to put all of an object's logic into one script. Instead, to understand how inheritance can be useful, it can help to look at how it's already being used in Unity. For example, scripts that can be attached to objects inherit from monobehavior, which is what allows event messages such as start and update to be called on them, and what allows your script to be attached to an object in the first place. But being able to be added to an object is not something that comes from the monobehavior class. This is because monobehaviors are not the only things that can be attached to objects. Components like audio sources, cameras, and lights, which are not monobehaviors, also need to be attached to objects. This functionality comes from the component class, which is the base class for anything that can be attached to a game object. Monobehaviors and most components also have an additional layer of inheritance between them and the component base class, the behavior class, which allows an object to be enabled or disabled. A couple of exceptions to this are rigid bodies, which can't be turned off, and 3D colliders, which implement their own enabled property in their base collider class, both of which connect directly to the component class, which in turn inherits from the object class, which is the top level, and the base class for all referenceable types in Unity. But why is any of this important? On an object level, it's generally easier to create logic by adding different scripts together that each enable a certain type of functionality and that each have a single responsibility. For example, to give an object health, to allow it to move or be moved, or to make it selectable. This is script composition in action, and if it's a good fit for the type of project you're making, it's generally a good approach for giving objects behavior, since it's flexible and very easy to change. This is why the player NPC enemy example isn't necessarily realistic. It highlights the point of inheritance well, but not how you're likely to actually use it. A general rule of thumb for identifying when inheritance is likely to be useful is when you recognize that you're writing the same code in different scripts because those scripts are the same kind of thing. For example, in my hobby project, the player object has a number of subsystems attached to it to allow the player to select objects, move them around, and delete them. This is script composition, not inheritance, but even though each of these systems work in a different way, they are all ultimately the same kind of thing. They're all player systems, and they all need a reference to the player class in order to work. This fits the use case for inheritance, since otherwise every time I made a new kind of player system, I'd need to write the same line of code to set up the player reference again. And importantly, if I ever want to change how it worked, such as logging a warning if the script is added to a non-player object, then using inheritance, I'd only need to do that in one place. So how does it work? First, I need to create a player system class. The expectation is that this class, or rather the classes that inherit from it, will be attached to objects as components. So this base class will continue to inherit from monobehavior, meaning that the classes that inherit from it will be monobehaviors as well. In the body of the class, I'm going to declare a protected reference to a type of player script. Protected variables and functions are publicly accessible but only to inheriting classes, meaning that other scripts can't access them. Alternatively, you can make the field public, which would also serialize it, meaning that it will show in the inspector. Base class variables are shown first, followed by derived class variables, which are shown after. Next, in the awake function, I can use a getComponent call to fetch a reference to the player class from the root object. This is all the base class really needs to do, and it's the functionality that all player systems share, at which point I can simply replace monobehavior with player system, and the script will get and will be able to use that player reference as if it was its own. However, while this works, there are a couple of extra steps that you may need to take. For example, I don't actually want the player system to be added to an object, just the scripts that inherit from it, since it doesn't actually do anything on its own. Making the class abstract means that instances of this class can't be created, and that the only way to use it is to inherit from it. Functions can also be made abstract, where an abstract function doesn't have a body, just a parameter pattern and a return type. It's then up to derived classes to implement their own version of that function, meaning that classes of that type will always have it, but will each implement it in a different way. However, in this case, I want the function to be called in the base class, so that the player reference can be set in awake. But chances are, some of my player systems may also need to use their own awake functions. This will hide the base class's version of the same function, meaning that it won't be called, and that the player reference won't be set. So how can you fix that? So long as it's accessible, meaning that the function is either public or protected, it's possible to call a base class's function using the base keyword. This allows you to call both functions from the inheriting class, which you'll typically do to extend a function instead of just hiding it and replacing it. Right now, however, the base awake function is being hidden by the derived class. While it is technically fine to intentionally hide a function with a new version, you typically won't want to do it in this way. Instead, you'll usually be better off by creating a virtual function in the base class, which is a function that can be overridden, and an override function in the derived class, which is an override of a virtual function, meaning that it will be called in its place. But how is that different to hiding the function? Why do the extra work? The reason that you're most likely to override a function instead of just hiding it is to do with polymorphism. Polymorphism is the use of a single interface to represent many different types. A common use for this is subtyping, which allows you to use a derived class in place of a base class. For example, there are many different types of collider, such as box colliders and sphere colliders, that each work in slightly different ways. On your object, you're likely to use one of these specific types of collider, while physics functions may specifically call for a general type of collider, the base class. This is possible using subtyping, where a sphere collider, for example, can be passed in place of a general collider reference and it will work. This can be extremely useful when you want to use a type of something, but you don't necessarily know what it will be exactly. But how does that relate to function overriding? If a script is expecting a reference to a base class, and gets a derived class instead, it will still call its functions from the base class that it inherits from. Meaning that if you hide a base function with a new derived version, the base version will still be called when dealing with a reference of that type. Instead, overriding the function allows a script that's expecting a base class, but that's given a derived class, to use the overridden version from the deriving class instead. As a result, even though the two methods appear to do the same thing at first, when replacing base class functions, you typically want to create virtual functions that can be overridden instead of regular functions that simply hide their base members. So far, you've learned about composition, which is the practice of adding single ability-focused scripts to an object to create functionality, and inheritance, which avoids duplication by sharing functionality in a hierarchical structure. Interfaces, in some way, can be considered as a mix of composition and inheritance, combining an ability focus with a kind of polymorphism that's similar to the subtyping that's seen in inheritance. The difference is that while inheritance and composition promote reusability by avoiding rewriting the same code over and over, interfaces create compatibility between different scripts that need to be treated as if they're the same. So what is an interface? In simple terms, an interface is a set of abstract functions that any class that implements that interface must use. Conventionally, interfaces are used to give a particular class an ability, so they're typically named for that ability, preceded by a capital I. For example, if you want to make something selectable, you could create an iSelectable interface. This works by creating an interface, not a class, that contains a select function with no body, just like when creating an abstract function. Then, to make something selectable, such as a light switch for example, all you need to do is implement the iSelectable interface by adding it after the class definition, or in the case of monobehaviors, after the base class separated by a comma. This will force the class to implement a public select function that has the same return type and parameter signature as the one that's defined in the interface. Put simply, the interface makes sure that you add the select function to the class, making it selectable. But why is that useful? Why not just write your own select function directly in a light switch class? After all, any script that implements the selectable interface will have to create its own select function anyway, so you're not avoiding duplication by using this method. So what is it good for? The point of an interface is that it forces a class to include functions of a certain type. Normally, if you create a specific reference to a specific type of class, then there's no real benefit to using an interface. Instead, an interface is useful because it allows you to refer to a specific class in a generic way, because of the functions it is guaranteed to have by implementing a particular interface. For example, a light switch, a door, and a chest might all implement the same selectable interface, meaning that they must all implement a version of the select function, which could be used to turn on the light, open the door, or search the chest. Each class implements its own unique version of the select function, and does something different when it's called. But even though each script is different, they all implement the same interface, meaning that the select function always has a void return type, no parameters, and is called select, meaning that they can all be treated by other classes as if they are the same, even though they're not. For example, instead of checking for a light switch or a door or a chest, the player only needs to check for scripts that implement the iSelectable interface, meaning that a selector script that gives the player the ability to select things only needs to try to get one kind of component, an iSelectable component, after which it can call the select function without even knowing what type of script it's calling it on. This is the entire point of interfaces, to create compatibility by forcing a script to include certain functions, allowing it to be treated generically, which can be useful for creating different kinds of pickups, selectable and interactable objects, and any kind of situation where you need to be able to treat different scripts as if they are the same. One example of this is state machines. While there are a lot of ways to make state machines, at a basic level, they typically work by executing different logic, but using the same triggers, which is why interfaces can be useful for creating them. For example, it's possible to create an interface-based state machine by defining a simple set of functions that will be present in each state, such as an update function or to process logic on entering a new state. These will be present in every state class, whether they're used or not. Individual states are created using separate classes that each implement the state interface. These are structs, not monobehaviors, because they need to be created as instances inside of another script. Finally, a current state variable that is a type of iState can be used to contain any class that implements the iState interface. It's this particular state that will be processed by the state controller, and that will always have its update function called. While this is a less conventional use for interfaces, it does highlight how they can be useful, as well as their similarities to inheritance, where, because both methods support a kind of polymorphism, it's possible to create a similar state machine using inheritance instead of interfaces. But even though there are overlaps, the use cases for inheritance and interfaces are different. Generally speaking, inheritance allows you to share the same functionality between classes to avoid duplicating the same code between scripts that are essentially the same kind of thing. While interfaces allow you to treat classes that work in different ways as if they are the same for the purpose of compatibility, allowing you to interact with many different types of system using a universal trigger, regardless of what it will do in response. Part of managing the relationship between scripts is restricting what any one class can do with another class's data. This can be a tricky thing to get right. After all, many of your scripts will need to communicate with each other in some way, so you'll need to be able to control how a class shares its data with other scripts that might need to read it or change it. There are several ways to do this. For example, it's possible to change or return data through public functions, or pass information to other classes through events. However, there may also be times when you want to let other scripts work with the class's variables directly. For example, let's say that you're creating a money value. Other scripts might need to change this value by adding to it or subtracting from it, or they may simply need to read it, in which case you could argue that making it public makes a lot of sense. This works, but chances are you'll want to do more than just set or read the value. For example, you might also want to add functionality that processes the value when it's updated, such as to make sure that it never goes above or below a set range. Or you might want to trigger an event that tells other classes that the money value has changed. It wouldn't be appropriate for other scripts to do this, since it's not their responsibility. And while you could do it with a function, let's assume that for now at least, you want to be able to access the variable directly. How can you control how other scripts interact with the value and what happens when they do? One method is to use a property. A property is a variable with explicitly defined actions for when you get it and when you set it. There are usually two reasons why you'd want to use one. One, to prevent a publicly available variable from being set by other classes, and two, to carry out additional logic when a variable is accessed without using a function as a go-between. So how do they work? A property is essentially one data value delivered using two variables, one that's public and one that's not. The private variable is the real value. It can't be accessed by other scripts, meaning that other classes cannot read or set it directly. Instead, the public variable, which will typically have the same name as the private field but capitalized, is used to get and set the real value. For example, the get function of a money float doesn't return its own data, it returns the value of its backing field. Likewise, the set function passes the new value to the real variable instead of using it for itself. In its most basic form, where the property simply passes values to and from the backing field, a property works in the same way as a public variable. Nothing is different. The advantage of using a property, however, is that it's possible to introduce additional logic before the value is read or set. And typically, this is where you might format the data before the real value is updated, or take the opportunity to execute additional logic, such as to trigger an event. Splitting the property between two variables is required when you're executing additional logic like this. But if all you want to do is make a variable publicly available, but prevent other classes from setting it, it's possible to do that with an auto-implemented property. Auto-implemented properties are useful for managing basic access, as they allow you to use a regular get with a private set. This can be useful when you need to give other classes access to your variable, but you definitely don't want them to be able to set it themselves, such as when creating a singleton reference. There's no need to explicitly define what happens in the get and set functions when using an auto-implemented property, and you don't need to make a second variable in order for this to work. However, it's important that if you do want to add extra logic into the get and set functions, that you don't do it with an auto-implemented property. This is because auto-implemented properties still use a backing field in the same way that regular properties do. The only difference is that you won't be able to access it. This means that there's no usable value for you to return or set, and if you try to use the front-facing property instead, you'll crash Unity. Properties can be extremely useful, but when are they useful? There's nothing here that can't be done with a public function, so why would you use a property instead? There's no one rule for using a property instead of a function, but as a general approach, it can help to consider how you want other scripts to be able to work with that data. For example, a money value might seem like a good fit for a property, and in many cases it is. However, you'll need to consider the level of control that you want other scripts to have over that value. For example, when using a property, any script can set the value to any number. The property manages how its data is actually processed, so there's not necessarily a problem with this, but it gives other scripts a lot of control. They can add, remove, or change the money value, meaning that the way another script is supposed to interact with it isn't actually that clear, even though it's just a simple number. While with a function, it's likely that the script will only be able to perform one or two tightly controlled actions, such as inputting a single value to change it, which is much clearer and easier to understand at a glance. Additionally, in this example, you might want to return data when trying to change the money value, such as returning a true or false boolean, if the transaction was actually successful. However, you might still want to allow other scripts to read the current value whenever they want, in which case combining a function with an auto-implemented property with a private set might make a lot of sense. But what if you also want to notify other classes when the money value changes? It makes sense to use the set method to do this. The set method is still private, but now that it's no longer an auto-implemented property, you'll be able to add additional logic to it, calling the event when the number is changed. However, it's entirely possible to invoke that same event from the function that changes the value in the first place, so why bother with a property? Why not just do it all in the function? The concept of single responsibility isn't necessarily restricted to just classes, and it can often help to consider if a function is sometimes doing more than it should. In this case, it makes sense to process the logic that only occurs when a value is changed with the mechanism that actually changes it, the set function. That way, if you wanted to add other functions that change the value in different ways, such as to reset it or to set it to an initial value, you wouldn't need to rewrite the code that triggers the event. And if you wanted to change it, because it only exists in one place, you wouldn't have to rewrite multiple functions. While the benefits of this may seem relatively small, you'd be surprised how easy it is to put everything that you want to do in one function, making the logic in your script a bit harder to change. And while I'd encourage you to use whatever method you find the easiest, knowing that properties exist and what they can be good for might help you to keep the logic and the data in your scripts a little more organized and a little easier to deal with. One of the hardest things to know for sure when you're writing your first scripts in Unity is if you're doing something in the right way. After all, it's only natural to worry if the things that you do now will negatively affect the performance of your game as it gets bigger. But what is bad performance anyway? When considering the performance of your code, you might be thinking about raw speed in frames per second and how the logic that you write might impact that. And while that is a consideration, it's highly likely that under normal circumstances, you're not going to create something that is inherently slow, so long as your code isn't extremely wasteful. In practice, this simply means avoiding excessive use of operations that you know can be slow, such as find operations or get component. While you can still use these functions, and you should if they provide a convenient solution to a problem that you're trying to solve, knowing that they're slow allows you to make a judgment call about when, where, and importantly, how frequently they're used. But, apart from being told, how will you know what's slow and what's not? There are generally 3 types of slow operation. For example, some operations simply take a lot of work, which is why find and get component can be slow, as they need to search through game objects to perform their task. For the same reason, you can generally assume that any operation that has to do something repeatedly has the potential to be slow if it does it enough times, such as cycling through large lists, loops, and arrays, or working with a large number of objects all at once. You will typically be able to tell when this could be a problem, since you will soon develop a feel for when something seems excessive. When this happens, the best approach is simply to be mindful of the performance impact of what you're doing, and if in doubt, test it by checking which part of your code, if any, has an exceptionally high impact on how fast your game runs. The second kind of slow operation is any task that reads or writes data from the disk. This typically has a short but high impact performance hit, and usually includes loading assets while the game is running. However, one of the worst offenders for this, purely because it doesn't seem like it would be, is debug log. Debug messages write to an actual log file on the disk, which is slow, meaning that you will typically want to disable log messages in your finished game. There are a number of ways to do this, but generally the most effective method is to create your own custom debug function and then make it conditional to the Unity editor. This will mean that for the finished game, the debug function and any reference to it simply won't be compiled. The last kind of slow operation, or at least a kind of operation that has the potential to cause performance issues, is anything that generates garbage. In simple terms, garbage is a memory allocation that is no longer used. This specifically refers to the managed heap, which contains referenceable allocations of memory that may be pointed to from multiple sources. Once a memory allocation has no references pointing to it anymore, it's now garbage. This is where the performance hit takes place. Heap memory can become fragmented because each allocation needs to be kept together, but may be a different size. As a result, making room for a new allocation typically involves either expanding the heap, or more often, clearing out garbage. Unity does this for you with the garbage collector, but doing so can cause CPU spikes and drops in performance. So how do you avoid garbage? Basically, any process that creates a reference to memory has the potential to cause garbage if it's then no longer used. Examples include creating and destroying objects, string concatenation, and creating new classes such as wait for seconds, which creates a small amount of garbage since it's technically a class. In comparison, newly created value types, such as structs, depending on their contents, and simple types, don't create garbage. This is because they're stored on the stack, not the heap, which is fast, one-in, one-out storage that lasts for the duration of a function's scope. This is why it's fine to create a new vector3 or a new ray, for example, even in an update, without worrying about performance. While small amounts of garbage are unlikely to impact your game, creating excessive amounts of garbage can cause performance issues. Most built-in functions that generate garbage will offer a non-allocating version as well, in which case if you need to call a method repeatedly that you suspect could cause garbage, checking for a non-allocating version can help to avoid garbage-related performance problems. If you're not sure if your code is creating any garbage, you can use the profiler to check how much is being allocated and which functions are responsible for it, as well as if any processes are contributing to a particularly long frame time. This general approach to performance, avoiding excessively wasteful operations, garbage, and frequently accessing the disk can make a big difference to how well your game runs, particularly if your project, for whatever reason, is sensitive to how well optimized it is. But, for the most part, unless your game is particularly performance intensive, or because you're targeting a low-power device, such as a phone, raw speed is unlikely to be the most critical factor in your game's performance. While most modern devices are able to bear the weight of performance inefficiency fairly easily, what they can't do is make up for errors and bugs that may exist in your game because of how it's built. A game that runs slowly can be frustrating, but unless you're being particularly wasteful, you'd do well to create a game that was so inefficient that it ran slowly enough to cause a real problem for most people. While bugs, on the other hand, that may make your game difficult or in severe cases impossible to play, are likely to have a much more significant impact on how well your game is perceived to run. As a result, in my opinion, it's much more important to focus on how easy your project is to work with for the purpose of making it easier to avoid and fix errors than it is to chase raw performance. By following the general approach in this lesson, you probably won't need to worry too much about the efficiency of your code, that is unless you're doing something in extreme quantities, at which point optimizations that would otherwise be minor may be more relevant than it would be when it's being used on one or two objects. These actions alone will go a long way to helping your game run efficiently, at which point it's more important that you focus on how manageable your project is. My advice is to do whatever it takes to keep your project manageable. Even if something feels like it's not the absolute best way to do it, a project that's easier to work with will perform better, even if it could run faster. At the end of the day, if your game is difficult to change, or if you don't have a good idea of what's happening in your scripts and when, then you're more likely to introduce bugs and errors that will be harder to find and harder to fix later on. After all, if your game is easy to change and runs without breaking, its speed can be improved over time. But if your game is full of bugs, or if it's too difficult to actually finish, a higher frame rate isn't going to help you. If you're new to writing code, it can be easy to assume that because programming looks complicated, that it's the syntax of a script that is difficult to learn. In fact, the programming language itself can be quite simple, or it is at least well documented, meaning that knowing how to write something isn't necessarily the difficult part. Instead, what can be tricky is knowing what to write in the first place. As a result, it can be easy to create code that is technically error-free, but that will make your project difficult to work with and that has the potential to cause problems as your game gets bigger and more complex. Luckily, there are many software design principles, best practice approaches, rules and guidelines that, when followed, can make writing maintainable code easier. However, you cannot follow them all, and you shouldn't try to. While design patterns and principles are meant to help you, the general idea of them is to allow a project to get bigger without becoming an unmanageable mess. After all, if your game is small enough, you can pretty much write it any way you want, and it will probably be fine. In contrast, trying to rigidly follow design principles because they are the right way to do things, without fully understanding why, can easily cause you to over-engineer your project. At both ends of the scale, the worst case result is likely to be that you won't finish your project. Without structure, your game can quickly become complicated, and you won't know how to progress it beyond a certain point, while following design rules too rigidly can prevent you from getting anything done, as you over-consider the hypothetical results of all of your actions. So what's the answer? How can you balance flexibility and structure? While there isn't a one-size-fits-all solution, a general approach is to understand the intentions behind the various rules so that you can break them with confidence. That way, when you choose to do something in the wrong way, because it's easier, you know exactly what risk you're taking and whether or not it's likely to cause you an issue. In this lesson, we're going to look at one of the most popular sets of design principles for writing maintainable code, Solid. This set of 5 general rules seems simple enough at first, but actually applying them as a beginner in Unity can be surprisingly difficult. So what are the 5 solid principles? How can they be used in Unity? And when should you be following them? The first of the 5 principles, the single responsibility principle, is probably one of the easier rules to apply to your own scripts. But even though its definition can be relatively straightforward, it's still easy to take this principle too far. The idea behind single responsibility is that a script should only have one reason to change. However, it's easy to assume that single responsibility means that each script only does one thing, which, if you take this advice too literally, can be very difficult to implement. After all, one thing can be very specific. Instead, the general idea, and the since clarified description of the single responsibility principle, is to keep the code that changes for the same reason together. For example, a movement script might move the player and make them jump. That is clearly two things, meaning that if you took single responsibility to mean one task, you'd need to create 2 different scripts. 3 when you realise that both of these systems require a ground check to work. In reality, trying to split these systems out can be more difficult than keeping them together. For example, they all use the same data, they may reference the same external components, such as a rigid body, and generally all do one thing, move the player. So is it okay to put them together? Ultimately, the definition of a responsibility is up to you, meaning that you will need to decide if any one part of this now combined system will need to be changed separately to the rest. For example, let's say that your movement system combines jumping, moving left and right, and a ground check. Would a non-controllable object in your game ever need to check whether or not it's grounded? If you have movable objects in your game that cannot be controlled, you might need to check whether or not they're touching the floor. In which case, you may choose to split out the ground check into a different component to avoid rewriting it. But now you have to find a way for the movement and ground check scripts to communicate with each other. In this example, if it's unlikely that you're going to create any kind of movable object that doesn't require a ground check, but you may need to create a groundable object that can't be controlled, then it's possible to split out the scripts without reducing their cohesion by using inheritance. For example, a groundable base class can be used to provide ground check functionality to both derived scripts, while the logic that allows an object to be controlled only appears in one. This works because this specific hierarchical relationship allows it to. An object is likely to only have one version of the script or the other, not both, meaning that the ground check won't be fired twice, and implementing it as a base class allows the movement script to use it directly, as if it was one of its own members, satisfying single responsibility, but without reducing cohesion. While this won't always be possible, it can help to remember that the idea of single responsibility is to make your life easier, not harder. Separating every class into different small parts just for the sake of adhering to a general rule may be helpful in some cases and unhelpful in others. After all, single responsibility is a two-way street, meaning that it's just as important to keep classes that do change together, while separating the code that may need to be changed or accessed independently in an appropriate way that's as convenient as possible. The open-closed principle stands for keeping a class open for extension but closed for modification. Generally speaking, this means allowing a class to be extended or added to, but without being fundamentally changed. You might assume that this is something that will only be relevant later on in your game's development, when certain classes that already exist have well-defined roles, meaning that they are relied on by other classes to work in a certain way and are essentially finished. However, while that is a relevant consideration, that only focuses on the closed part of the principle, not the open. Open for extension means that you can add functionality to the script, but there are 2 interpretations as to what that actually means. Meyer's open-closed principle, introduced by Bertrand Meyer in his 1988 book Object-Oriented Software Construction, suggests the use of inheritance to extend the functionality of a class without affecting the original, or any other scripts that might rely on it. However, the principle has since been redefined into a more general polymorphic open-closed principle, where abstraction through an interface allows you to make a class modular through the use of a generalized output. But what does that actually look like in Unity? A closed script is well defined, meaning that it has a core purpose and offers limited public accessibility, typically through public functions. At this point, changing the script means changing how it works, which, while you may need to do that, has wider reaching implications, especially if the script is already being used in your project. As a result, you should only need to go into the class if you actually want to change what the class does or how it does it. Not if you want to extend it, meaning do more of what it already does. For example, let's say that you have a script that detects a collision with collectible objects. To detect a pickup, you might try to get a specific pickup script, such as a points pickup. Technically, this is not open for extension, since if you plan to have the player pick up a different type of collectible that uses a different script, you will need to go back into the collector class to check for both types. While this example is simple and relatively harmless, creating a situation in which you have to change a class just to allow it to do more of what it already does can cause issues. In this case, because the class isn't open to extension, because you have to manually change it to extend it, it also can't be considered closed. The solution is to generalize the class's output, in this case by using an iCollectible interface, which would allow you to add new pickups that implement the same interface, or through inheritance, which would allow the collector to pick up different objects using subtyping. In Unity, there are many different ways to generalize the output of a class, such as with interfaces, inheritance, Unity events, and delegates, but in all cases, the general idea is the same, that you should only need to change a system if you actually need to change the system, and simply extending it to do more of what it does shouldn't affect how it works. The Liskov substitution principle is a guideline for using inheritance correctly, and it requires that you must be able to use a derived class in place of the class that it inherits from. If you're already using inheritance in an appropriate way, that is, if the relationship between a subtype and the class it inherits from is already hierarchical, then you're probably already adhering to this principle and you don't need to worry. However, it's possible to use inheritance in a way that seems like it should work, but actually doesn't, in which case the Liskov substitution principle is a good test to check to see if your hierarchy is appropriate. In simple terms, when you create a subtype, you should be able to pass it in place of the type it derives from. An example of this is the various individual collider classes which can be used in place of their hierarchical parent, the collider. Any of the specific collider types can be passed in and used as if they are a type of collider. The only functionality that may be missing is any additional logic that only exists inside of a specific collider type. This adheres to the substitution principle. So what does a violation of the principle look like, and why is it a problem? A violation of the principle is realistically going to be a relationship that seems hierarchical but isn't, at least not in the sense that a derived class can be used in place of its parent. For example, let's say that you have a human class, then an adult class, and then a child class. This may appear hierarchical, but in the context of inheritance, it's not. An adult is a type of human, but a child is not a type of adult, meaning that a child class could not be used in place of an adult, since children cannot do everything that an adult can do, such as going to work, paying bills, or fixing the toilet. This inappropriate hierarchy can be exposed by checking for an is-a relationship, where the child is not a type of adult, but is a type of human. A lot of the time, this will be all that you need to do. But the relationship between your scripts may not always be as clear, in which case the is-a check may not be enough. One way of demonstrating this is with the circle-ellipse problem, sometimes referred to as the square-rectangle problem. In this example, the circle is a type of ellipse, meaning that it is hierarchically correct that the circle inherits from the ellipse. But an ellipse can be uneven in shape, meaning that its width or its height can be different from one another. A circle can't do this, but because it inherits from ellipse, it needs to be able to. This is where the Liskov substitution principle comes in. A circle is a type of ellipse, but because a circle cannot be used in place of an ellipse, it violates the substitution principle, exposing an inappropriate hierarchy. One possible solution is to reverse the relationship, which makes more sense since the ellipse is basically a circle that can do more, in this case by being extended in width. However, there may still be functionality that a circle provides, such as calculating its radius, that an ellipse couldn't. The Liskov substitution principle is useful as a general test to see if the hierarchical relationship between two classes is appropriate. If it's not possible for a derived class to be used in place of the class it inherits from, meaning that it can't do at least everything that its parent class can, then the relationship is inappropriate. Typically, this may mean that you will need to change the structure of your inheritance, in this case by having circle and ellipse inherit from a shape class instead, or use a different approach entirely. The interface segregation principle states that classes should not implement functions that they don't use. That's pretty much it. The idea here is that in order to make a class universally accessible, you might be tempted to use an interface that contains more functionality than any one object needs. The downside of this is that objects will then implement functionality that they don't actually use, which can be confusing, since when they're accessed, they will appear to offer functions that will more than likely be empty. For example, you might create an enemy interface to deal with the different functions that may apply when interacting with a type of enemy, such as damaging it or stunning it. This would work in that it allows you to create multiple types of enemy that each respond to common enemy functions. But it's possible that not all enemies can be stunned, or you might want to use the same interface that allows you to damage an enemy, but to damage an inanimate object instead. In which case it's generally good practice to use multiple smaller interfaces, such as iDamageable and iStunnable, in place of a larger general purpose interface, allowing you to use the functionality you want while leaving out the logic you don't. In Unity, the benefits of interface segregation are similar to the benefits of single responsibility, and typically you're more likely to run into this issue with components than you are with interfaces, depending on how you're building your game. However, it's still typically a good idea to limit the functionality in your interfaces, especially since they are easy to combine together again. For example, if you still wanted to combine the damageable and stunnable interfaces, you could do that by either implementing both interfaces into a class that uses them, or by creating a combined interface that itself implements both the damageable and stunnable interfaces into one. A possible exception to the interface segregation principle is when you're intentionally using interfaces to create fixed compatibility between classes that are meant to be used interchangeably. An example of this would be state machines, where by design, each state may or may not use a particular function, meaning that it may be empty. While this could be a problem if you find yourself creating very specific functions that are meant for just one state but not the others, offering the same set of functions between different state classes is kind of the entire point of an interface-based state machine. Meaning that while it technically appears to break the segregation principle, so long as each function is relevant to all state classes, it's not necessarily a problem, even when a state doesn't need to use it. The dependency inversion principle is generally quite simple but can be easily misunderstood, which can be a problem, as overusing this principle without fully understanding the point of it can cause you to over-engineer your code. Generally, the point of dependency inversion is to prevent a high-level script from depending on a low-level system. But what does that actually mean? Let's say, for example, you have a class that uses an instance of another class, whether that's a monobehavior or typically a plain class that exists inside of the high-level system. For example, I once worked on a game where I wrote a dynamic music system, where the music player created an instance of a music sequencer when it was running and then passed data to it. The player needed the sequencer in order to work, but the systems were different enough that they deserved to be in separate classes. In this case, the high-level class controls the low-level system, meaning that it directly communicates with the publicly available functions and variables of that system, which works, until you want to change part of it, at which point you'll need to change the low-level system and the controlling class, since it communicates with it directly. This is where a high-level class becomes dependent on a low-level one. The solution is to create an abstraction between the two classes. The music player sends information to a kind of sequencer, but so long as it's able to accept the format of data it's providing, it doesn't care exactly what it is. While the sequencer receives data in the same format, but doesn't need to know where it came from. This creates flexibility through generalization, by allowing the controlling system to use a different low-level system of the same type, and vice versa. This can be useful for swapping out different parts of the system without having to rewrite anything, and for testing, where a test script can now be connected to either part of the system to see if it works as expected. But this principle isn't just about abstraction, since if it was, it would overlap quite heavily with the open-closed principle, which already encourages abstraction to make classes more easily extendable. So when does the inversion part happen, and why is it important? The reason it's called dependency inversion is because under normal circumstances, even though the higher level system controls the lower one, it's the lower level system that sets the rules. If the signature of its functions or its data changes, the higher level system must change as well in order to meet the new requirements, otherwise it won't be able to use it. In which case the higher level system is dependent on the lower level class, violating the dependency inversion principle. The dependency is inverted when the connection is abstracted. This happens because the higher level system owns the abstraction, typically an interface, meaning that it sets the rules of interaction that a lower level system must follow in order to be used by the controlling class. Put simply, the script that is in control now also sets the rules. This loosens the coupling between the two scripts, making either part that little bit easier to change. However, it can be easy to overuse or misinterpret this principle, in which case it's important to identify when you should consider using it. As a general rule of thumb, look out for any scenario in which you create a close relationship between a high and low level class, particularly if it feels like you're writing one script in two places, as this may be a good indicator that one class is dependent on the other. In which case, ask yourself if it makes sense, in this example, for the higher level class to also control the rules of that interaction. If it does, then it might be worth creating an abstraction between the two classes. In the purest sense of the principle, this typically means using an interface, but if you're applying it as a general guidance in Unity, it could also mean using events or messages to broadcast data in a passive way. This achieves the same outcome, where the two scripts are not directly connected, and the controlling script decides what data lower-level classes will need to be able to accept. With all of the solid principles, while they can be useful, it is extremely important that you use them as guidelines only. If you try to rigidly enforce all of your code to all 5 of the solid principles, then it's possible that you will never finish your project, since you're likely to spend most of your time over-engineering your code, ultimately making it harder, not easier, to work with. Instead, use the solid principles as a guide to double-check the structure of your project or to help you to decide between multiple options when you're not sure which is best. And if doing things in a different way would be easier for you, or makes more sense based on how you're building your project, then so long as you're aware of the solid principles and the intention behind them, you can be confident when choosing to go against them.